Absolute zero is the lower limit of the thermodynamic temperature scale, a state at which the enthalpy and entropy of a cooled ideal gas reaches its minimum value, taken as zero. The theoretical temperature is determined by extrapolating the ideal gas law, by international agreement. Absolute zero is taken as minus 273.15 degrees on the Celsius scale, which equates to minus 459.67 degrees on the Fahrenheit scale. The corresponding Kelvin and Rankine temperature scales set their 0 points at absolute zero by definition. It is commonly thought of as the lowest temperature possible, but it is not the lowest enthalpy state possible, because all real substances begin to depart from the ideal gas when cooled as they approach the change of state to liquid, and then to solid, and the sum of the enthalpy of vaporization and enthalpy of fusion exceeds the ideal gas's change in enthalpy to absolute zero. In the quantum mechanical description, matter at absolute zero is in its ground state, the point of lowest internal energy. The laws of thermodynamics dictate that absolute zero cannot be reached using only thermodynamic means. As the temperature of the substance being cooled approaches the temperature of the cooling agent asymptotically, a system at absolute zero still possesses quantum mechanical zero-point energy, the energy of its ground state at absolute zero. The kinetic energy of the ground state cannot be removed. Scientists have achieved temperatures extremely close to absolute zero, where matter exhibits quantum effects such as superconductivity and superfluidity. Thermodynamics near absolute zero. At temperatures near 0 K, nearly all molecular motion ceases and delta S equals zero for any adiabatic process where S is the entropy. In such a circumstance, pure substances can form perfect crystals as T0. Max Planck's strong form of the third law of thermodynamics states the entropy of a perfect crystal vanishes at absolute zero. The original Nernst heat theorem makes the weaker and less controversial claim that the entropy change for any isothermal process approaches zero as T0. The implication is that the entropy of a perfect crystal simply approaches a constant value. The Nernst postulate identifies the isotherm T equals zero as coincident with the adiabat S equals zero, although other isotherms and adiabats are distinct. As no two adiabats intersect, no other adiabat can intersect the T equals zero isotherm. Consequently, no adiabatic process initiated at non-zero temperature can lead to zero temperature. An even stronger assertion is that it is impossible by any procedure to reduce the temperature of a system to zero in a finite number of operations. A perfect crystal is one in which the internal lattice structure extends uninterrupted in all directions. The perfect order can be represented by translational symmetry along three axes. Every lattice element of the structure is in its proper place, whether it is a single atom or a molecular grouping. For substances which have two stable crystalline forms, such as diamond and graphite for carbon, there is a kind of chemical degeneracy. The question remains whether both can have zero entropy at T equals zero even though each is perfectly ordered. Perfect crystals never occur in practice. Imperfections, and even entire amorphous materials, simply get frozen in at low temperatures. So transitions to more stable states do not occur. Using the Debye model, the specific heat and entropy of a pure crystal are proportional to T3, while the enthalpy and chemical potential are proportional to T4. These quantities drop toward their T equals zero limiting values and approach with zero slopes. For the specific heats at least, the limiting value itself is definitely zero, as borne out by experiments to below 10 K. Even the less detailed Einstein model shows this curious drop in specific heats. In fact, all specific heats vanish at absolute zero, not just those of crystals. Likewise for the coefficient of thermal expansion. Maxwell's relations show that various other quantities also vanish. These phenomena were unanticipated. Since the relation between changes in Gibbs free energy, the enthalpy and the entropy is thus, as T decreases, delta G and delta H approach each other. Experimentally, it is found that all spontaneous processes result in a decrease in G as they proceed toward equilibrium. If delta S and, or T are small, the condition delta G less than 0 may imply that delta H less than 0, which would indicate an exothermic reaction. However, this is not required. Endothermic reactions can proceed spontaneously if the T delta S term is large enough. Moreover, the slopes of the derivatives of delta G and delta H converge and are equal to 0 at T equals 0. This ensures that delta G and delta H are nearly the same over a considerable range of temperatures and justifies the approximate empirical principle of Thomson and Berthelot, which states that the equilibrium state to which a system proceeds is the one which evolves the greatest amount of heat, i.e., an actual process is the most exothermic one. One model that estimates the properties of an electron gas at absolute zero in metals is the Fermi gas. The electrons, being fermions, have to be in different quantum states, which leads the electrons to get very high typical velocities, even at absolute zero. The maximum energy that electrons can have at absolute zero is called the Fermi energy. The Fermi temperature is defined as this maximum energy divided by Boltzmann's constant, and is of the order of 80,000 K for typical electron densities found in metals. For temperatures significantly below the Fermi temperature, the electrons behave in almost the same way as at absolute zero. This explains the failure of the classical equipartition theorem for metals that eluded classical physicists in the late 19th century. Relation with Bose-Einstein condensate. A Bose-Einstein condensate is a state of matter of a dilute gas of weakly interacting bosons confined in an external potential and cooled to temperatures very near absolute zero. Under such conditions, a large fraction of the bosons occupy the lowest quantum state of the external potential, at which point quantum effects become apparent on a macroscopic scale. This state of matter was first predicted by Satyendranath Bose and Albert Einstein in 1924-25. Bose first sent a paper to Einstein on the quantum statistics of light quanta. Einstein was impressed, translated the paper from English to German and submitted it for Bose to the Zeitschrift für Physik, which published it. Einstein then extended Bose's ideas to material particles in two other papers. 70 years later, in 1995, the first gaseous condensate was produced by Eric Cornell and Carl Wieman at the University of Colorado at Boulder NIST JILA lab, using a gas of rubidium atoms cooled to 170 nanokelvin. A record cold temperature of 450 plus or minus 80 pK in a Bose-Einstein condensate of sodium atoms was achieved in 2003 by researchers at MIT. The associated black body wavelength of 6,400 km is roughly the radius of Earth. Absolute temperature scales. Absolute, or thermodynamic, temperature is conventionally measured in kelvins and in the Rankine scale with increasing rarity. Absolute temperature measurement is uniquely determined by a multiplicative constant which specifies the size of the degree. So the ratios of two absolute temperatures, T2, T1, are the same in all scales. The most transparent definition of this standard comes from the Maxwell-Boltzmann distribution. It can also be found in Fermi-Dirac statistics and Bose-Einstein statistics. All of these define the relative numbers of particles in a system as decreasing exponential functions of energy over kT, with K representing the Boltzmann constant and T representing the temperature observed at the macroscopic level. Negative temperatures. Temperatures that are expressed as negative numbers on the familiar Celsius or Fahrenheit scales are simply colder than the 0 points of those scales. Certain systems can achieve truly negative temperatures, that is, their thermodynamic temperature can be of a negative quantity. A system with a truly negative temperature is not colder than absolute zero. Rather, a system with a negative temperature is hotter than any system with a positive temperature, in the sense that if a negative temperature system and a positive temperature system come in contact, heat will flow from the negative to the positive temperature system. Most familiar systems cannot achieve negative temperatures because adding energy always increases their entropy. However, some systems have a maximum amount of energy that they can hold, and as they approach that maximum energy, their entropy actually begins to decrease. Because temperature is defined by the relationship between energy and entropy, such a system's temperature becomes negative, even though energy is being added. As a result, the Boltzmann factor for states of systems at negative temperature increases rather than decreases with increasing state energy. Therefore, no complete system, i.e., including the electromagnetic modes, can have negative temperatures, since there is no highest energy state citation needed, so that the sum of the probabilities of the states would diverge for negative temperatures. However, for quasi-equilibrium systems this argument does not apply, and negative effective temperatures are attainable. On 3 January 2013, physicists announced that they had created a quantum gas made up of potassium atoms with a negative temperature in motional degrees of freedom for the first time. History. One of the first to discuss the possibility of an absolute minimal temperature was Robert Boyle. His 1665 new experiments and observations touching cold articulated the dispute known as the primum frigidum. The concept was well known among naturalists of the time. Some contended an absolute minimum temperature occurred within Earth, others within water, others air, and some more recently within nitre. But all of them seem to agree that there is some body or other that is of its own nature supremely cold, and by participation of which all other bodies obtain that quality. Limit to the degree of cold. The question whether there is a limit to the degree of coldness possible, and, if so, where the zero must be placed, was first addressed by the French physicist Guillaume Montans in 1702. In connection with his improvements in the air thermometer. In his instrument, temperatures were indicated by the height at which a column of mercury was sustained by a certain mass of air, the volume, or spring, of which varied with the heat to which it was exposed. Montans therefore argued that the zero of his thermometer would be that temperature at which the spring of the air in it was reduced to nothing. On the scale he used, the boiling point of water was marked at +73 and the melting point of ice at 51. So that the zero of his scale was equivalent to about -240 on the Celsius scale. This close approximation to the modern value of -273.15 degrees Celsius for the zero of the air thermometer was further improved upon in 1779 by Johann Heinrich Lambert, who observed that -270 degrees Celsius might be regarded as absolute cold. Values of this order for the absolute zero were not, however, universally accepted about this period. Pierre-Simon Laplace and Antoine Lavoisier, in their 1780 treatise on heat, arrived at values ranging from 1,500 to 3,000 below the freezing point of water, and thought that in any case it must be at least 600 below. John Dalton in his chemical philosophy gave 10 calculations of this value, and finally adopted -3,000 degrees Celsius as the natural zero of temperature. Lord Kelvin's work after James Prescott Joule had determined the mechanical equivalent of heat. Lord Kelvin approached the question from an entirely different point of view, and in 1848 devised a scale of absolute temperature which was independent of the properties of any particular substance and was based on Carnot's theory of the motive power of heat. It followed from the principles on which this scale was constructed that its zero was placed at -273.15 degrees Celsius. At almost precisely the same point as the zero of the air thermometer. Very low temperatures, The average temperature of the universe today is approximately 2.73 kelvins, based on measurements of cosmic microwave background radiation. Absolute zero cannot be achieved, although it is possible to reach temperatures close to it through the use of cryocoolers, dilution refrigerators, and nuclear adiabatic demagnetization. The use of laser cooling has produced temperatures less than a billionth of a Kelvin. At very low temperatures in the vicinity of absolute zero, matter exhibits many unusual properties, including superconductivity, superfluidity, and Bose-Einstein condensation. To study such phenomena, scientists have worked to obtain even lower temperatures. The current world record was set in 1999 at 100 picokelvins, or 0.000000001 of a Kelvin, by cooling the nuclear spins in a piece of rhodium metal. In November 2000, nuclear spin temperatures below 100 pK were reported for an experiment at the Helsinki University of Technology's low-temperature lab. However, this was the temperature of one particular degree of freedom, a quantum property called nuclear spin, not the overall average thermodynamic temperature for all possible degrees in freedom. In February 2003, the Boomerang Nebula was observed to have been releasing gases at a speed of 500,000 km per hour for the last 1,500 years. This has cooled it down to approximately 1 K, as deduced by astronomical observation, which is the lowest natural temperature ever recorded. In May 2005, the European Space Agency proposed research in space to achieve femtokelvin temperatures. In May 2006, the Institute of Quantum Optics at the University of Hanover gave details of technologies and benefits of femtokelvin research in space. In January 2013, physicist Ulrich Schneider of the University of Munich in Germany reported to have achieved temperatures below absolute zero in gases. The gas reportedly became hotter rather than colder. In September 2014, scientists in the CUORE collaboration at the Laboratory Nazionale del Gran Sasso in Italy cooled a copper vessel with a volume of 1 cubic meter to 0.006 kelvins for 15 days, setting a record for the lowest temperature in the known universe over such a large contiguous volume. In June 2015, experimental physicists at Massachusetts Institute of Technology have successfully cooled molecules in a gas of sodium-potassium to a temperature of 500 nanokelvins. By cooling these molecules a bit further, it is expected to exhibit an exotic state of matter.